Welcome back to Arts Learning. In this video, we'll be going over the law of universal gravitation, as well as how this relates to other topics like mg, force of gravity, right? Which is mg, but this is a different force of gravity here. It's more universal, okay? So we'll be going over that, as well as gravitational fields we'll cover in a later video. So if you're looking for that, that'll be in one of the later videos. When I cover electric fields, I'll go along with that as well. But for right now, we'll just go over the concept and the formula associated with it. So Newton's law of universal gravitation. Newton proposed a law, force is equal to big G, not the little g we're accustomed to, times big M times little m over r squared. If you remember the Coulomb's law formula, this looks very similar, right? So the Coulomb's law was just K times Q1 times Q2 over radius squared. Almost exact same in how they represent, right? Same, like G and K are, abstract values, M and M. These are values here that you multiply together that can change. These are masses, right? And Q1, Q2, masses. So very similar. And then both are inversely related to distance, as you can see here, okay? But the G here, so K, if you remember, was 8.99 times 10 to the 9, right? But G here is just going to be 6.67 times 10 to the negative 11. That's going to be what I'll use, okay? There are more detailed approximations, but this is what I will use. And something you need to know about gravity, right, is that masses are always going to pull on each other. There is no repelling force in gravity. So if you think about the Earth, so this is the best Earth I can do. And then it's going around a sun, right? But before that sun, what do we have rotating around ourselves? The moon, right? The moon. What force is pulling the moon towards us in that orbit? So it's a circular orbit, which I'll go over why it's a circular orbit, centripetal force. But what's the force here that's pulling the moon towards us? Gravity. Similarly, we're pulled across the sun in that same gravitational field, okay? Gravity is always attraction between two objects. It's a force of attraction. There is no repulsion like charges, okay? So think about it as being perpetual, unlike charges, always attracting each other, no repulsion at all, okay? So that's how gravity works and how it's different from regular charges, right? So it's always attractive and masses pulled together. That's why the field lines are also going to look a bit different for this, but we'll go over that in a bit, in a later video, okay? So yeah, G, you need to remember that's Newton meter squared per kilogram squared, which will just cancel out with these two to give you Newtons for force. R is just your distance, right? Distance from center. Now, why I specified center is because if you had, this Earth, right? Just the Earth here. The force of gravity between the Earth and the Moon is the distance between their centers. I mean, not the force isn't the distance, but the D value, the R value here that we plug in, is the distance between their centers. Okay, their centers of mass, their centers. So that's what we're going to plug in for R. Similarly, if you were standing on the Earth, it would just be, the Earth's radius. But here it would be obviously something larger. And then big M is just the first mass. Little m is just the second mass, okay? Both are masses. One doesn't need to be bigger than the other, but yeah, they're just both masses, right? We just denote them as mm, capital M and lowercase, because Oftentimes we use a larger mass and a smaller mass, like a planet and a human, or something along those lines. But there is gravitational force between planets as well. Okay? And gravity is the only force that attracts in space, right? It's what causes a lot of interactions. Like black holes are just sucking in gravity, right? They have a large gravitational pull. So gravity is what drives everything in space, and this is how you measure that. Okay? And that's all you need to know about this formula. Now we'll go over how to use them. And G, big G, right, is not a little g. Little g is an acceleration, which is 9.8 meter per second squared. And big G is used in the formula for universal gravitation, and it's 6.67 times 10 to the negative 11. Okay, and then these weird units, you'll understand why they're the units, right? If you multiply these two and this, it has to give you a Newton. So let's try an example. The Earth is 5.97 times 10 to the 24 kgs. The Moon is 7.35 times 10 to the 22. And they're both 3.84 times 10 to the 8 meters apart. We need to find the gravitational force. The force is just big G, big M, M over R squared, right? So force is just, what's big G gonna be here? 6.67 times 10 to the negative 11. The mass is times 5.97 times 10 to the 24. That's our larger mass anyway. And the moon's mass is 7.35 times 10 to the 22, right? And then all of that over our distance squared, which is going to be about, so this thing, 3.84 times 10 to the 8. And then we're going to have to square that, right? So when it says this, it means the centers, okay? Because you measure these distances in centers, not like this distance, but this distance. Okay? You plug these in. I'm not going to use units here because it's going to get a bit messy if I do that, but it should give you approximately 1.99 times 10 to the 20 newtons. Okay? So let's try a few problems. Two 1,000 kg cars parked 2 meters apart. Find the gravitational force between them. So these are obviously rarer circumstances because the thing is, you know how force is equal to big G, big M, M over R squared? We rarely see this happen, right? Because gravity is the force of attraction. It isn't really just you fall down when you jump up. It's a force of attraction. The earth is attracting you and pulling you back. In the earth's scenario, that works because the earth has a large enough mass to actually render a large force, right? But think about it. If we had just two small cars, then their masses wouldn't be comparable to a large force, right? They're just small cars. They don't have masses enough to attract each other. Because as you can see here, this G is 6.67 times 10 to the negative 11. How are they going to counter this 10 to the negative 11? They're going to need a large enough mass, right? So, and a close enough distance. So that's why we don't see gravitational as attraction in everyday life, but in space it's seen more because then the scale you're looking at becomes larger, right? So this big M and this M becomes larger as well. So you get a larger force, okay? So now let's try solving for this gravitational force. So force is equal to big G, 6.67 times 10 to the negative 11, times big M, which is 1,000. And they're both 1,000, so I can just put 1,000 again. All of that over 2 squared. So this is about 6.67 times 10 to the negative 11 times 10 to the 6, right? 6 zeros, over 4, or 6.67 times 10 to the negative 5 over 4. Which if you plug in right, should give you around I believe, 1.67. I'm going to round up to the second digit, times 10 to the negative 5. Okay? And there you go, in newtons. So pretty straightforward, not too complicated there. One of the lesser difficulty questions, okay? Now, let's try the second one. A 70 kg person stands on Earth's surface. Okay, so this is one of the more prominent forces, right? Because for the previous one, you saw 1.67 times 10 to the negative 5 newtons. That's why you don't see it, right? That's why objects don't float near each other in everyday life. But trust me, it happens a lot in space. That's what gravity is. It's the force of attraction. That's why the gravitational force was that formula. So here, a 70 kg person stands over here. Okay, from the center of Earth, he stands at the radius. We need to find the weight of this person as well as the acceleration that weight implies. So if we take into account 70 kgs, right? 70 kgs is our mass. The weight is our mass times little g, right? So that's going to be mass 70 times 9.8, which is about 687 newtons. Okay? And your acceleration is just your force over your mass, right? Your force here is 687 newtons. And your mass here is 70 kgs. So your acceleration will land about 9.8 meters per second squared. So the thing here is, you can see how, acceleration you already know, right? It's going to be the acceleration to gravity. You didn't really need to do all this math. I'm just showing you that it lands you at the same place. So you can see that we didn't really need to use the big formula, right? Which makes sense because we didn't get the mass of our person. We did get it, but it's too complex to plug into this, right? It doesn't make that much of a difference to plug in here. Because when you have a big G, a big M, a little m, and an r squared, when this m is like small compared to this big M, so you can see how my mass, 70 kgs, is nothing compared to the mass of the Earth, right? So then you can basically ignore this. This becomes your gravitational force. And if you plug in these values, you should get the same answer. You'll get the same weight and same 9.8. Okay? So if you plug in big G, big M, and r squared, you'll get the same 687 newtons. But then you might need to do a bit more math for the acceleration. Okay? All right. So a planet has surface gravity 9.8 meter per second squared at a radius of 6.37 times 10 to the 8 meters. Find its mass. So the mass, if we rearrange the equation for force, right? We know that was force is equal to big G, big M, M over R squared, right? Force here is just gonna be mass times acceleration, right? And so mass times acceleration, but you can't really plug that into this because then it's gonna become like, you might cancel the masses here, but you're still left with not much. You can't do much with this, right? But you do know that M here, right? Big M, which is about, let's see, 6.3. We don't know big M. Actually, what was I even doing? Yeah, we don't know big M. We're going to multiply that with big G, 6.67 times 10 to the negative 11. And then we're going to divide that by r squared, which is 6.37 times 10 to the 6 squared. And that's going to be equal to our acceleration, right? Because force ma, we can divide both the m's here. Our acceleration, we know that's going to be the acceleration due to gravity, which is 9.8. Okay? So you plug and you chug here. M is equal to 9.8 times 6.37 times 10 to the 6 squared divided by 6.67 times 10 to the negative 11. So now let's see what this is going to give us. So this is a bit of a hassle to plug into a calculator, right? And it should give you about 5.96 times 10 to the 24, which is a coincidence because that's the exact mass of our Earth. That makes sense, right? Mass of our Earth is going to be the gravity on Earth, which is 9.8 meters per second squared. This gravity, it doesn't exist. I mean, it might exist, but it doesn't exist in our known out of this planet scope, okay? The other planets have a higher gravity or lower gravity. So now let's try this one. Two masses attract. You double their separation and triple one mass. By what factor does the force change? The original force is big G times m big M times little m over r squared. Your new force, so force nu I'll write here, is you double their separation, so over 2r squared, right? Because this r is separated by 2. It's doubled by 2. You pull it twice as far apart. And then big G times 3m times 3 of one mass times the other mass. So in other words, this is just 3 GMm over 4r squared. But you know, this entire expression, GMm over r squared, it's just the force, right? The original force here. So then it's going to be 3 over 4 times that, right? 3 over 4 times that. So we know that the factor that the force changes by is 3 over 4. I just took the coefficients out, right? I just plugged in Fg for this expression. Whatever was left, I just turned that into the coefficient. So it decreases by a factor of 25%, and it retains 75% of its value. So by a factor of 3/4, right? Next video, we'll be going over circular motion as well as centripetal acceleration. And if you're wondering how gravity makes planets stay in motion, how it makes planets go in circles, then stay tuned for what's about to come, okay? And now, so yeah, we'll go over this next video, and give me a like and subscribe so we can continue on this physics journey and continue helping others. Thank you.